All right, the law of conservation of momentum. So the law of conservation of momentum basically reads the same way that any law of conservation you would think should read. So it states that the total momentum in an isolated system is conserved. So because of that, we can convert this into mathematical equations. So we can say that the momentum total of the input, and that's a vector, is equal to the momentum total final. And that's going to go for any number of objects involved. So it doesn't have to be just 2. It could be more than 2. It could be 3, 4, 5, 6, however many there are. Could be one thing hits 2 things or 2 things hits 1 thing. If we said this curling disc over here was 1, so this little curling puck is 1. Do you call it a puck? I don't know what you call it. And this one over here is 2. The formula of momentum is mass times velocity. So I can say if it's traveling this way, the mass initial, or mass 1, velocity 1 initial, is the same as mass 2, velocity 2 initial. And there's, of course, a proof for this. So let's go down here to this proof. So the proof states that when the 2 objects collide, they each exert a force on the other. So M1 applies a force on M2 of force 1, 2, force initial 2. Likewise, M2 applies F2 initial on M1. So they're both applying force on each other, is what this is saying. Those forces are saying the same thing. So if we use Newton's third law, we can say the force initial of 2 is equal, made the sign wrong, used to making those vector signs, is equal and opposite to the force 2 initial. So, with all that said, we can make the following statement. Provided there are no other forces, It's an isolated system. The mass of one, acceleration 1, is equal to the inverse of mass 2, acceleration 2. So mass 1, acceleration is velocity 1 final minus velocity 1 initial over change in time is equal to the inverse mass of 2 times velocity 2 final minus velocity 2 initial all over change in time. We can distribute and cancel change in time. So we're going to get mass 1, velocity 1 final minus mass 1, velocity 1 initial is equal to negative mass 2, velocity 2 final plus mass 2, velocity 2 initial. We can simplify this and get rid of some of the negatives to make this a little bit better. And so when we simplify this and make it a little bit neater, mass 2, velocity 1 initial plus mass 2, or mass 1, I'm sorry, mass 1, velocity 1 initial plus mass 2, velocity 2 initial is equal to mass 1, velocity 1 final plus mass 2, velocity 2 final. So there's our proof. So it says a curling rock, if we're over here, hits an identical initially stationary rock with a velocity of 5.11 meters per second east. After the collision, the first rock is now stationary. What is the velocity of the second rock after the collision? All right. We know that momentum is conserved. The curling rock 1 hits 2 with this initial velocity, and then it stops. And we can't lose momentum. Momentum has to be conserved. So the second identical rock has a velocity, a final velocity of 5.11 meters per second east, or the same as the initial velocity of rock 1. What assumptions did I make? So what assumptions did I need to make for that to be true? The first thing I had to assume, and the main thing I had to assume, was that there were no other forces. So there's no friction, there's no force of air, there's no air resistance. We're assuming this system is completely isolated. And what happened to the kinetic energy of the first rock? We haven't talked about kinetic energy yet. We're going to get to that. But kinetic energy is essentially energy in motion. So that kinetic energy, or that energy of movement of rock 1, so the kinetic energy of rock 1 was transferred to rock 2. All right, that is all of conservation of momentum. So that is what the loss states. We're going to apply it on the next PowerPoint.